There we go. I will begin. So, so you had a question about some of the problems on the exercise sheet. Is that right? Which one? Mm-hmm. Well, I'm just going to throw it out, so might as well. There you go.
I've got mine.
All right, well, which one?
I just I don't know, just one or two stuff, the solve ones.
The solve ones?
Just one, I don't need a lot.
And they got every
Catch my brain.
and they teach you how to design.
All right.
You only go to that class once a week. And then that teacher, he counseled classes. I think he
All right, let's solve this problem. This is like exercise 1, but it's not exercise 1. All right, so I'll try to make up some examples today that are similar to the exercise sheet, but different. All right. We have a quiz. When? Wednesday. That's right. Okie doke. So, how do you think we should solve this problem? Common denominator. So that would be 56, right? So I've got 8x over 56 minus 7x over 56 equals to 2. What's 8 minus 7? It's 1, right? So we've got x over 56 equals to 2. And then multiply by 52. We've got x equals to 112. I'll call that example 1. Something what? You want something more funky? Okay, very good. So let's do something like example 2. I'll try something like 3 over x plus 8 equals to 2 plus x over 9. There's no exercise like this on the sheet, but it is something you should be able to solve. Because the techniques to solve this are the same as the techniques we use. Like basically what we do, something like this, is we use cross multiply, right? Like, so I do 3 times 9 is equal to, 2 plus x times x plus 8, right? And that, I think we can solve, right? So that's going to be 27 is equal to x squared plus 10x plus 16. How do we solve something like that? What do we do? Say what? Combine like terms. Okay, so I'm going to take your combined like terms and say, so we want to put everything on one side, right? So make it z equal to 0, right? So what's 16 minus 27? Negative 11 equal to 0, right? Nice. Wow. Wow. You don't understand how epically lucky this is. Because that we could factor it. You got to understand, guys, I just made this example up. Like I just randomly chose these numbers and just put that there. The likelihood of that giving us a quadratic equation which you can factor like this, they're not high. We are very, very lucky this problem worked out nice. Man. Well, anyway, so then what? Right, yeah, take the opposite. So x equals to minus 11 or x equals to 1 are potential solutions. The reason I say potential is because we got to check, you know, whenever we do like the cross multiply, there's a chance that we have changed the equation a little bit by multiplying by something that could be 0. Like when you multiply something that could be 0, you can sort of destroy and create information in a sense. So that cross multiply step is something you got to watch out for. Now, technically speaking, I know it's not going to be an issue because the cross multiply step is only troublesome when x equals to minus 8, which is not where we're at. So like I'm pretty sure these are both going to work, but just to double check our answer, let's try it out. Let's check. So we've got 3 over minus 11 plus 8. What's that equal to? 3 over minus 3, right? So that's equal to minus 1. And how about the left-hand side? I mean the right-hand side. So this is left-hand side, right? Right-hand side, we've got 2. I'm checking x equal to minus 11 to start with, right? So 2 minus 11 over 9 is minus 9 over 9, which is also equal to minus 1. So, hooray. Indeed, minus 11 solves it, right? And if you think about x equals to 1, likewise, x equals to 1, we've got, 3 over 1 plus 8, and that's 3 over 9, and equals question mark, 2 plus 1 over 9, well, that's 3/9, right? So when I'm checking the solution, sometimes I use different notation. Like sometimes I will separately evaluate the left-hand side and the right-hand side and then see that they match. Other times I'll just write one equation which shows that they match. Like there's different ways to show that to denote the checking. That's why you see me write it like this sometimes. I put a question mark over the thing I'm not sure about yet, and then a check usually once I say, oh, okay, it works. I want to show you how lucky we were in this example. Let me change the numbers ever so slightly. Example 3. So suppose we had 2 over x plus 7 is equal to, I don't know, x minus 1 over 5. If this one works out too, I'll be angry. But because then I'll go home and try to do it again, it won't work. But cross multiply, we get 10 is equal to x minus 1 times x plus 7. Multiply it out, we got 10 is x squared plus 6x minus 7. Oh, I'm very gullible. Let's see here, don't do that to me. 6x minus 17. I think we're free and clear. I don't think this one's going to factor nice, right? And I mean, can you factor that? See, but you guys remember we have talked about how to solve quadratic equations already, right? So we should probably Cross it out and not do it? No. I was going to say complete the square, right? So at the moment, I think this is an example of a problem that might appear on like the final, but possibly not test 3, because this is a combination of the test 3 material and the test 2 material, right? In test 2, we learned how to solve quadratic. I mean, part of test 2 was solving quadratic equations, right? Am I wrong? You can disagree. I know I had completing the square on test 2. Didn't I also have find the solution? Yeah. So let's just go ahead and solve it. I would try to make the problem on your next quiz or test more like example 2, but by the end of the course, I'd like you to be able to solve example 3. Okay? So let's work it. So this is, I mean, there's two paths we can go down here. We could use the quadratic formula, right? Or we can complete the square. I'm going to encourage completing the square for a variety of reasons. So this is x plus 3 squared. And then I have to do what? I have to subtract the square of 3, which is 9. So that's x plus 3 squared minus 26. Now, at this point, you can either factor and read the zeros off the factorization, right? Let's do it that way. So this is x plus 3 minus the square root of 26, x plus 3 plus the square root of 26. So the solutions are x equals to minus 3 plus or minus the square root of 26. So that's one way to look at how to solve the problem, right? An alternative way, if you don't like this factoring way, another good way to look at it is to go from here and to go, okay, well that means that x plus 3 squared is equal to 26, right? And so then by taking the square root of both sides, we get x plus 3 is equal to plus or minus the square root of 26. And so x is equal to minus 3 plus or minus the square root of 26. Like that's another legitimate way to find those same solutions. You want to look at it as factoring? Do you want to look at it as, isolating a square and then taking a square root, allowing for the plus and minus possibility? The third way, of course, would just be to use the quadratic formula. But I don't recommend that. Because I think the advantage of completing the square, there's other advantages here, right? Like, think about the separate problem. If I asked you to graph y equals to x squared plus 6x plus minus 17. Have we done that? Have we graphed quadratics in here? We may not have. I know we have in my pre-calculus class. I think we might not have actually done that in this class. I think that may be a chapter 7 topic, actually. The graphing of the quadratics. Like, what graphing have we done in here? We've done lines earlier, right? Mm-hmm. And like, just, I give you a function. I say find the domain and the range, right?
And what's the point of the intersection?
Point of the intersection, right?
Create a line that...
What's that? Intersection point. But I haven't actually given you stuff like, here's a polynomial, graph the polynomial, right? That's not something we do in this course. That's pre-calculus. We do that in pre-calculus. What's that?
That's when you graph polynomials, do it have to be straight, or be like U-shape or something?
Yeah, it can be like a cubic is kind of like an S. Yeah. Or if it's even power, it's kind of like a U. Yeah. And then all kinds of other stuff can happen. But now, what I'm about to tell you, this is not on your not on the quiz Wednesday, right? But this is useful information for the final exam. Not final exam part 1, but actually final exam part 2. but it's this, is like to graph, if you want to graph y equals to ax squared plus bx plus c, if you can look at it as y is equal to a times x minus h quantity squared plus k, then what that means is that the vertex is at the point h comma k. And basically it either opens up or down from there, you know? So my point to you is just that, and this value happens to be c. C is the y-intercept, right? And this, I'm assuming that a is positive. If your vertex instead was like over here, and your a was negative, it would open down, right? And these are like different basically parabolas. You know, if we look at y equals to this quadratic, it's a parabola that opens up or it opens down. And some of this algebra we've already been doing, like completing the square. See, completing the square on this quadratic in this previous example actually would show me if I was to graph y equals x squared minus 6x, x squared plus 6x minus 17. From completing the square, I could read the vertex off of that. I could tell you that the vertex is minus 3 minus 26. So like there's another benefit to completing the square as it relates to graphing parabolas. We'll talk more about that after the test, okay? But just while we're here, I thought I should pause and make a comment. So my intention, if things go as I planned them, on the quiz 3 and test 3, your problem should not be like example 3. It should be like example 2. In other words, once you do the cross multiplication, like the quadratic that you get to, it shouldn't be one of these complicated ones where you need completing the square and square roots and junk. Unless it's like really simple. Like I'm okay with you ending up with a quadratic like this. You know, if this is your quadratic, okay, I think you should be able to get, that's a bad example, that's just plus or minus 3. What if it was 6, you know? Like I think you should be able to solve that on test 3, quiz 3. Because the solution is what? Plus or minus root 6, right? Like I think that kind of quadratic I think is still fair game. But this is something I'd like to postpone until like final exam part 2 to be tested, okay? All right, let me stop talking about that kind of thing. Let's see if we can find another problem. Is there another particular one you'd like me to make one like?
So are all these, or not all these specifically, but stuff like these going to be on the test? Like
These are all,
this page?
well, there was another one we had from before. It was the, there's 2 ones that are relevant to, I feel like there's another one, isn't there? There's also the chapter 5 one. I should have posted these both in course content. If I haven't, I'll try to do that before I leave today.
This is the last one I got. This is also quick one.
I'll tell you guys in a second here. Let me. The other one's from sections like 5.1, 5.2, 5.3, 5.4. So the one I'm looking at right now is section 5.5 and chapter 6. The previous exercise sheet, which is also relevant to quiz 3, is 5.1 through 5.4. And I should have them both posted in course content. I will check. Uno momento. Huh. Well, so in course content, I have the previous exercise sheet posted, but I have not posted the one we're looking at right now. Sorry about that. So actually, in course content, I have the other one.
Yeah. Mm-hmm.
let's see here. I can, unfortunately, the projector's not working, so I can't put them up, but I can, I mean, I'll refresh your memory. Uh-oh. I end up standing up sideways from this chair in such a way that it messes with my back. I have to be careful. Otherwise, I'll be with a cane the rest of the semester. Let's see here. Okay, so at the start of the last exercise sheet, I had questions about domain of a function, remember? Listen, we'll come back to quadratics and treat chapter 7 as a whole systematically from start to finish as soon as test 3 is done. So I think that would be next. Basically, one day we'll be able to do everything that's there. So that should be, I think, Thursday after the test, right? Because the test is next Tuesday, isn't that right? Make sure I'm saying this right.
Next Monday?
Yeah, I'm sorry. I'm Tuesday, Thursdaying you guys. What's wrong with me? Yes, quiz 3 is Wednesday. Test 3 is next Monday. Very good. And then Wednesday next week, I will cover chapter 7. Right. And again, we've covered a lot of chapter 7 already as we've been going this semester. Okay, so this one from the previous exercise sheet, this is exercise, where'd you go? What on earth? Oh, there it is. Find the domain of the function was one, right? Find domain of f of x equal to, say, x plus 3 over 2x minus 7 in interval notation. So can we do this? What is the domain for a function? Right? If you have a formula, the domain should be all x for which the formula is reasonable. So what do we need for this formula to make sense? We need 2x minus 7 to not be equal to what? Two x minus 7 not equal to what? 0, right? 0 gets us into trouble because then we have division by 0. We must avoid that. So that gives me 2x is not equal to 7, which gives me x is not equal to 7/2. So that's the x which we must avoid. So what's the domain of f? Minus infinity to 7/2, not included, unioned with 7/2 to infinity. That would be the domain in interval notation. Now, the other kind of problem we had in the previous exercise sheet was simplification. We had tons of simplification problems, right? Here's a simple one that's kind of like one we had. Something like 30x to the 7th divided by 6x to the, x squared, something like that. Simplify, And so what do you do there? What's 30 over 6, 5. So we get 5. X to the 7 minus 2, right? So we've got 5x to the 5. That would be the answer here, right? Simplify that expression. And there were more interesting simplification problems that required factoring, right? Like x squared. Here, I'll do a version of one that's like something on the test, but like something like in the exercise sheet, but different. So we had something like x squared minus 64 over x squared plus 16x plus 64. Is that right? Wait a minute. Ooh, wait a second here. Yeah, 6 plus 64. Simplify that, you know. So how do you simplify something like that? Well, you factor the denominator and you factor the numerator, right? How does the numerator factor? Yeah, x plus 8 times x minus 8, right? How does the denominator factor? Yeah, x plus 8, x plus 8. Very good. And so what's the simplification we can make here, right? Right, yeah, these cancel. And we're just left with x minus 8 over x plus 8. And there you go. So I might make the instructions something like simplify by factoring, you know, the denominator and the numerator, cancel out any common factors. I might put that as instructions if I wanted to make sure if I wanted to try to guide you guys in the right direction, I might make those the instructions. Let's see here if I can find another example, kind of like, let's see here. We had another exercise we did was something like x to the fifth, fifth, listen to me now, x squared minus 16 over 3x plus 9 times, you know, x squared plus 6x plus 9 over, you know, x plus 4. That was another kind of problem, more or less like that. How would we do it? I mean, again, factor x squared minus 16 is x plus 4 times x minus 4, right? We can factor a 3 out of this one. 3 times x plus 3, right? And that one, that's x plus 3 squared, right? And of course, we still got the x plus 4, right? And then you can start, you know, reducing the expression by canceling like factors, if you see them. In this case, we've got this x plus 4 can cancel that x plus 4. This x plus 3 can cancel that x plus 3, right? And all we're left is what? So 1/3 x minus 4 times x plus 3. That's how that one simplifies. Or you could also write it, so Maya, that would be the same as if I wrote it x minus 4 times x plus 3 over 3. Like that's the same answer. Is that what's bugging you? Yeah, we've always got this choice, right? When we've got the stuff divided by a, we can either write it like that, or we can also write it alternatively as 1 over a times the stuff. I mean, that is a choice that we can make notationally. Those are equal. But if you're not looking for it, it can be hard to see the equivalence of two expressions because of that, you know? I mean, totally agree that that's a thing that can hang people up on. Let's see here. So another example that would be from the previous exercise sheet, and I'm glad you guys are asking me to remind you about this because I think it's healthy. So we could have something like something like 1 over x plus 3 over 1 over x minus 7. That's like another simplify that. You know, how would you simplify that? Get them out of the top and bottom. So you mean to get the fractions out of the top and bottom somehow? I mean, I usually tell people I want to clear out the fractions. And so to do that, I look for like a, you know, a common thing I can.
Put it over 1 and get them to the common. Do we not just need to get the bottom to the common denominator?
Well, the thing is, I can't do that unless I have, I think what you're thinking about is this, right? Which is, was it stay, keep, flip? How we guys say something like this? Flip, keep, stay. There's some, keep, change, flip. That's the one. So keep, change, flip is kind of like this, except you keep A over B, and then you flip the C over D. And that's what this is equal to. Keep, change, flip. Not that I advocate these kind of rhymey things, but if it helps you, great. But the thing is, I can't do that here. This is trouble, because I don't have fractions, right? I've got 1 over x plus 3. I've got 1 over x minus 7. Like, I can't just do the flippy-floppy thing. Unless I make these into fractions, then I could do it. But there's an easier way. Like, I would advocate for this, just looking at what you can multiply it by to get rid of the fractions. So like, I look at this and I go, I'm just going to multiply by x over x. So if you just multiply this by x over x, you're in business. We can do that because it's 1. And when I do that, I get distributing, you know, x times 1 over x plus, you know, 3 times x divided, I guess I should say 1 over x times x, given the order in which I wrote things. Like that. And then, of course, x over x is 1, and I just, what do I have? I've got 1 plus 3x over 1 minus 7x, yeah? Now, we could engage that keep, change, flip way of thinking about it. Like, that's an alternative way to work this problem. And I think it's probably helpful for you to see me work through it that way. Let me do that. We have a minute, right? So, let's see here. So 1 over x plus 3 over 1 over x minus 7. So if I want to make the numerator and the denominator into fractions, I need to make a common denominator for the top and a common denominator for the bottom, right? Just so happens x. So I make a, you know, this is 1 plus 3x over x, right? And this is 1 minus 7x over x. then I can keep change flip. And then the x's cancel. And lo and behold, we get the same answer. What if instead of having the same thing in both fractions, you had like different divisions? What if you had very similar, but what if you had like 1 over x plus 3 over 1 over x minus 2 minus 7? How would that go? If you wanted to simplify that, what would you do? Let me make this an x squared just to be more annoying. How would you simplify something like this? Yeah, if you want to go the multiply by way, what would you do? I got to multiply the same thing top and bottom, right? I'm going to put an x squared there because we definitely want that. And also a x minus 2 because we also want to cancel that out, right? I mean, that's the least common multiple of x squared and x minus 2 is x squared times x minus 2. And so if you multiply that out, what do you get? We get 1 over x squared times x minus 2 plus 3x squared times x minus 2. 1 over x minus 2 times x squared times x minus 2 minus 7x squared times x minus 2. So I've done nothing there but distribute through the multiplications. And of course the cancellation is different upstairs and downstairs. Like upstairs x squareds cancel, and we're left with x minus 2 plus 3x cubed minus 6x squared. Downstairs the x minus 2 cancels, and we're left with x squared minus 7x cubed plus 14x squared. And that, I mean, you could rewrite it in descending order or something, but that's about as simple as it gets. I mean, now if we did the keep change flip way of doing it, we would just make like a denominator for the top, a denominator for the bottom, and then use the keep change flip to do it.
Would it still come back to the
I think so. I mean, I hope so. This would become what? Common denominator upstairs. We have 1 plus 3x squared over x squared, right? Divided by 1 minus 7 times x minus 2 over x minus 2. So then keep change flip that thing. 1 plus 3x squared over x squared times x minus 2 over, what does that work out to? 14 plus 15. Minus 7x, yeah. Interesting. So in the numerator, I see I've got my x minus 2 plus 3x cubed minus 6x squared, which you can compare. I mean, that's the same numerator, right? But the denominator, Oh, I'm an idiot. Look at that. I could have simplified the denominator, couldn't I? 14 plus 1 is 15. So we actually have 15x squared minus 7x cubed. So yeah, they do. They're the same. Mm-hmm. You gotta go? Okay. By the way, this is probably harder than what's on the test. Like, this is not something that was in the homework. It's a little bit, I'm basically combining a couple different homework problems as I make this. This problem's pretty tough relative to your homework, assigned homework. So this to me feels more or less like a bonus question in here. All right, let me see if I mean, it's been a while since we did these simplify problems, so it's probably good to review some of them, right? Let me do something like your exercise 16. The mathematical malpractice to not put this on your test or something like it, because it's just such an easy problem that illustrates whether or not you're thinking, clearly. And so this one's really, it's a nice problem. It doesn't require a lot of thinking. And so something like 8x to the 10th minus 7x to the 4th plus x cubed divided by 2x squared. Simplify. So the point is, we already have a common denominator, so we can break a sum up in the numerator without worries, right? I mean, this gives me 8x to the 10th over 2x squared minus 7x to the 4th over 2x squared plus x cubed over 2x squared. And so answer, 4x to the 8th minus 7 halves x squared plus 1 half x. And then, if I ask this question, it's very likely I ask a follow-up question like, and the instructions would be simplify, if, simplify as much as is possible, something like that would be the instructions here, right? So if I said simplify as much as is possible, x squared over 3x squared plus 4x cubed plus 10x to the 10th, what would you do? So what do you guys think? How would I simplify this one? Can I break the sum? I mean, the answer is no, because the sum is in the denominator, and we have no property of algebra allows me to break up sums in denominators like that. There's a big difference between the sum or the difference being in the numerator versus the denominator. 3/5 plus 1/5 is 4/5, right? 3 over 3 over 7 is not equal to, this is equal to 3 over 4 plus 3, right? But that is not equal to 3 over 4 plus 3 over 3 or anything like that. You can't break up sums in the denominator. It just doesn't work that way. That's not how arithmetic works. And algebra, of course, is built over truths we find in arithmetic. And so, what can I do though? I could factor x squared out of the denominator, right? X squared factors out. What do we got? X squared times what? 3 plus 4x plus 10 what? X to the what? Eight, right? And then we've got a common factor upstairs and downstairs. We can cancel those. Yep. And we get 1 over 3 plus 4x plus 10x to the 8th. So, you know, it seems entirely likely that I ask a pair of questions kind of like this. To see if you understand the difference between an addition in the denominator versus an addition in the numerator. Because it's one of those fundamental truths that I'd like to kind of like build into you as you leave this course, right? We can't mess with sums and denominators without special happenings. Let's go back to the other exercise sheet. Let's work some of the more interesting ones over there. All right, so rationalize denominator. So I'll do 2 examples of this. One, I'll do something like 3 over 2 plus root 7. How are you going to rationalize the denominator there? The instructions would likely be simplify by rationalizing the denominator. So what do we multiply this by to get that radical out of the denominator? Say again? No. How about this? 2 minus the square root of 7 over 2 minus the square root of 7. That should do it. So if we do that, what do we get? So you guys have a formula sheet, so I would encourage you to, like make a list of how we rationalize different denominators, right? There's at least 3 different patterns, maybe 4, depending on how you divvy things up. I mean, and then 3 of those are, I would say there's 3 distinct techniques that tend to occur. The one is the one I'm doing right now, which is just change one of the radicals to minus and multiply by that. The other one is just to multiply by the radical. I'll do that one next. And then the third is with the complex number case, but that's really the same as this. It just appears to be different notationally. So I get 6 minus 3 root 7. Downstairs, I've got a 4 plus 2 root 7 minus 2 root 7, so the root 7's cancel. And I have minus the square root of 7 squared, right? Which of course is just 7 again. So these guys cancel. And we've got 6 minus 3 root 7 divided by 4 minus 7. In other words, that's 6 over minus 3, which is minus 3 root 7 over minus 3. So pretty nice. The answer is minus 2 plus the square root of 7. Does the original number look like minus 2 plus the square root of 7 to you? It doesn't look like that to me, but that's what it is. Funky. A simpler example is something like this. Rationalize 7 over the square root of 3. how would we rationalize that? Well, that we just multiply by square root of 3 over square root of 3. That's what you're thinking about? Ah, cool. So that is the first kind of example. I really should have led with this example, but oh well. Hindsight is 2020. Although hindsight is 2020 seems like a phrase that should just completely vanish from our lexicon. Given the events of 2020, I think, like, referring to 2020, like 2020 vision, does that expression even make sense anymore?
2021 vision should be what.
2021 vision is what you want? Yeah. I don't know. Unless you just like to live in fear all the time, I guess. I don't know. Maybe. All right, 7 over 9 times root 3. There you go. I would like to live a less fear-based existence. I mean, I already do, but I would like for everyone else to get on board with that idea.
So is the top one, like the one right above that you didn't square off, is
Uh-huh.
that not the same answer as the other one?
This one?
No.
That one?
The other problem. Is that not the same as the thing below?
Ah, yeah, I mean, 6 of one, half a dozen of the other. I mean, yeah. Potato, potato. Sure, why not? Now, there's another problem like this. Let me warn you guys. So the other thing that came up was something like this. 13 over the square root of 2 plus the square root is, I don't know, 5 or something. So to simplify that, it's the same as the first one. Just multiply by minus. Flip the sign on one of the radicals, and things should work out nicely for you. So that'll gives me 13 root 2 minus 13 root 5 upstairs. And downstairs I get root 2 squared plus, root 2 root 5, or minus root 2 root 5 plus root 5 root 2 minus root 5 squared. And so, of course, these guys cancel. And we've got 2 minus 5, which is what? That's funny. So the denominator here has again worked out to minus 3, but for very, very different reasons. That's funny. 13 squared 2, it amuses me. But I'm easily amused, so there you go. The other kind of rationalizing denominator example is complex numbers, right? So if I have something like, say, 3 over 7 plus I, how would I, put that into Cartesian form? Usually the instructions I would give here is rewrite the complex number such that it's in Cartesian form, a plus bi. Right? Rewrite in Cartesian form. A plus IB. So this is not Cartesian form, right? So what you do is multiply it by 7 minus I over 7 minus I. And we get 21 minus 3I divided by 49 plus, minus 7I plus 7I minus I squared. Of course, the i's cancel downstairs. Minus I squared is 1. So what you got is 21 minus 3I divided by 50. 49 plus 1 is 50. And so one more step, that's 21 over 50 plus I times minus 3 over 50. So sometimes when I ask the question, I'd say find values for A and B, which put the complex number in Cartesian form. If I ask the question that way, then the answer would be A equals to 21 over 50. and b is equal to minus 3 over 50. Those are the so-called real and imaginary parts of the complex number. 3 over 7 plus I. So. All right, let's try to solve one of these radical problems. So the quiz 3 and test 3 should be a mix of what? Of simplification problems and solve problems, right? I like solve problems because there's a certain clarity there. And I mean, simplification, there's always a kind of, I don't know. Let's see here. So example, try to pick the hardest one. Just probably the hardest one. X minus 8 equals to the square root of x minus 6. It's more or less the hardest one. I guess I could have made it harder. I could have said x is equal to 8 plus the square root of x minus 6. Solve that, right? If I did that, the first thing you would need to do would be isolate the radical, right? And that would get you to x minus 8 equals the square root of x minus 6. Then what should I do? Did I ever check that the audio was working?
Yes, work. It says something.
La la la.
Yeah, it's working.
Okay, good. It's a little bit late to ask that, isn't it? But so how about we take this and we square both sides, right? If we square both sides, we get x minus 8 squared equals the square root of x minus 6 squared. What's the square root of x minus 6 squared? Well, it's x minus 6. Yeah, very good. And then this FOILs out to x squared. Yeah, plus 64, right? I'll take that 64, and then minus 16 in the middle because the minuses, right? And that's equal to, so then we put it all on one side, we get x squared minus 17x plus 70. By the magic of problems that are coming from the book, it factors nicely. Like if I just make up numbers and write an equation that looks like this, it will bring us to a quadratic formula, a quadratic equation, which is nasty. But because this is one that's taken from your homework, it solves nicely, and it is x. You can factor this one, is my point. All right, 10 and 7, plus or minus? Minus and minus, right? So that x equal to 10 and x equals to 7. That's right. These are potential solutions. And here, the fear is real because when we squared the equation, we could have adjoined new solutions, right? That's the trouble. And let's check it out. I mean, x equal to 10, does it work? 10 minus 8 is equal to 2. Is that equal to question mark the square root of 10 minus 6? Well, that's the square root of 4, which is equal to 2. Looks like we're okay on x equal to 10. What about x equal to 7? 7 minus 8, negative 1. Is that equal to question mark? I mean, we already know no. Minus 1 cannot be equal to a square root. Square roots are positive, right? Because we talk about the principal square root. And I shouldn't put a check mark there. I should put a no, not equal. I mean, well, that's equal to 1. The point is that this is no, not a solution. So